Hi guys, let's get started. So today we're going to talk about the encoder and decoder architecture. It's a very popular language processing technique that has been widely used nowadays. It was first published in 2014, and it still holds the state of art in the field of natural language processing. So let's take a close look at it. The problem that the encoder and decoder framework tries to solve is a sequence-to-sequence problem. Here I got a simple example. It's a sequence prediction problem. So given a sequence of inputs, I was trying to predict the next characters in the sequence, or I was trying to classify this sequence into some kinds of categories. A simple example will be if I have a sentence, my name is Samuel Deep Learning 11 / I'm gonna trying to predict the next word in the sentence. If I have this sequence feeding into my model, a possible result will be 785, since this is gonna be the next character here. But what's a more complicated question, as Professor just mentioned, talk about today, is sequence to sequence. So let's say if I have a variable length sequence and I was trying to convert it into another variable length target sequence, that's going to be a more complicated problem. An example will be if I have a French says picture visit India last December. I don't know how to pronounce this in French, but I was gonna translate into the English version. Picture visit India last December. Another example will be if I have an audio file. This will be the audio images, audio wave images of my audio, and then I was trying to convert it into a sentence. Say my heart is in the work. So the problem of this sequence-to-sequence problem is the trick is that it's variable length to variable length. So the length of the input sequence is not necessarily the same as the sequence length of the output sequence. The order of the input sequence is not necessarily the same as the order of the output sequence. So keep that in mind. The length and the order is not necessarily the same. I know a lot of you guys are laughing at this, but this course workload seems to be very low this semester. This is the English version. If we were trying to convert it into Chinese, we find out that the sequence of the input and the output is different, and the order of the words is also very different. That is to say, like this course, the first two words in the input sequence is not necessarily meaning the first two characters in the output sequence. So the idea is that, especially in language translation, different languages have different grammars. They have different ways of using subject and verbs. So it's not necessarily that the first or the second words correspondingly to the output sequence order. So that's a very hard problem to fix. And here comes the encoder and decoder architecture. Like I said, it was first published in 2014. It was used in the statistic machine translation. It has become the state of art language model ever since then. And it can be applied to many fields. The one that we are interested in is use it as a language model and together with RNN. And we're going to see that this framework is going to be capable of learning languages both semantically and syntactically, so meaning that it's going to understand what the language is saying, and it's also going to understand the syntax for the sentence. So the architecture for the encoder and decoder is relatively very simple. So the model will consist of two RNNs work as encoder and decoder separately. What the encoder tries to do is to map the variable length of the input sequence into a fixed length vector representation. So let's say if I have a file of sentence that I want to, like a file of the English sentence I want to translate into a French. So the input will be each sentence will be the English sentence, say my heart is in the work. And we're gonna fit this into our encoder, and the encoder gonna get the fixed length for each sentence, no matter what's the length of it. So let's say if I have a sentence has length of 10, I'm gonna get the embeddings at, let's say, the dimension of 256. And if I have a sentence of let's say 1,000 words, I'm still gonna convert it into a vector of dimension 256. So that's the point. We're gonna convert the variable length sequence into a fixed vector representation. And then next, we're gonna feed this embeddings into our, sorry guys, I made a mistake. This is actually gonna be the decoder. This is gonna be the decoder. And then next, we're gonna fit this embeddings into our decoder networks. What the decoder network's gonna do is it's gonna max the fixed length vector representation back to the variable length, the target sequence, and the two networks gonna be trained jointly to maximize the join probability, the conditional probability of the target sequence given the input sequence. So the general idea is that given if I have a English sentence, my heart is in the work, I first convert it into a fixed length, and then through the decoder, I'm gonna convert it back. I'm gonna convert it back to a French version. What we are trying to maximize is the probability of this thing. Let's call it x prime, or let's call it y. This is gonna be our x. So what we are trying to maximize is the a condition probability of the y given the probability of the x. We don't have another pen, but the probability of the y given the probability of the x, that's what we're trying to maximize. The idea of the encoder and decoder framework is going to be feeding the input sequence into the encoder step by step. I was talking about the time step. So let's say if I have 10 words, there's a time sequence there. If I say my name is Deep Learning 11785, so there are 6 words in this sequence, and there's a time sequence. There's a time series there. You cannot put the name in front of my, because that doesn't, the whole sentence won't make any sense. So there's the idea is that there's a time sequence in the input sequence, and we're gonna fit in them by the time sequence into our RN code. And then once we get the embeddings, we're gonna have the embeddings for each time sequence, and then we're gonna take that embeddings, feed in time step by time step into our decoders to get the target sequence here. So the input sequence feeds into the encoder at each time step, and the embeddings generated for each time step, and the embeddings feeding into the decoder and generate target sequence step by step. So what we're trying to maximize is the y1, y2, until yt, given the probability of x1, x2, and x until xt. That's a conditional probability we're trying to maximize here. Any question as a step? There are, there's, there are a lot of stuff that can be applied to the encoder and decoder model. Attention is one of the most frequent used thing that you can use in the encoder and decoder model. And also we can apply teacher force, for example. Remember here we are feeding each the A and B and C into the encoder and decoder thing, and we are using this the output to predict together with the previous embeddings to predict the target sequence at this time step. We can also just use the grand truth to predict this. This is called teacher force. So the ratio that you want to use the grand truth versus the predictions from your own network, the ratio is called teacher force. And that's a widely used technique that you can improve your network's learning abilities while you are training your language models.
Could you repeat that? The ratio between what?
So remember when professors are talking about the sequence-to-sequence model, while we fit into this, this area is our decoder network. So this W is actually coming from the previous one, right? But what we can do is that instead of feeding the W from the previous one, we can feed it from the ground truth. So the marker is, okay, that would be great. Oops, sorry. So if I have a this will be my encoder. Here, it's okay if you grab me another marker. Sorry about that. This will be my encoder, and then I have a. Can you guys even see that? No. Okay, I guess I'm just gonna type this. So let's say if I have my heart is in the work as my input sequence, and then I'm gonna get a dimension of the embeddings. The dimension of my embedding is gonna be 1 and then 124, 1024. For my embeddings, and then the targets thing gonna be my ha t the vowel. I was trying to generate the French version, but apparently that's not the French version. But whatever. So this is gonna be my input. This is gonna be my target sequence. So what the encoder and decoder thing really do is it's gonna fit in this sequence into the encoder framework, into the encoder network, and then we're gonna get the embeddings. Thank you. And then we're gonna get the embeddings. It's actually gonna be 5. We have 6 words here. Each of the embeddings is gonna be the size of 1024. So we're gonna get 6 embeddings, and then we're gonna fit the 6 embeddings step by step into our decoder network. And then this decoder network gonna give us this sentence. The way that we know that when to start is to have the normally people will just add the start symbol at the beginning of the sentence and the end symbol at the end of the sequence. So normally what people does is that it fit in the first my embeddings into the decoder. It's not the my, but the start. It fits in the first start embeddings into the decoder, and the decoder has that thing, and it can produce the next words from the embeddings. Let's say my, And then you're going to use this mice embedding to predict the embedding for the heart, and then and then this thing. And until it generates the end, it will continue to generate the word until it meets the end character here. If it's not, if it still has not met the end character, then it will never stop. So that's how we can generate variable lengths of the encodings there. But we were trying to predict this from the work that from our own decoder network. What the teacher force does is that you're gonna feed in the embedding for the mice together with the networks that I have for the embeddings I have for the mice from my decoder network. So I can either use this my embeddings my from the ground truth, or I can use the embeddings from my decoder to predict the next word heart. The ratio is that if I use I can say 10% of the words I'm going to use the ground truth, and then 20% of the 20% of the time I'm going to use the ground truth. So I was talking about this ratio. Does that make sense? Okay. No worry about that. You guys gonna apply this technique in your homework 4. Teacher 4 is gonna largely improve the performance of the network, and you will be very clear at that time. So I was just trying to give an example, so I was not prepared for that. But like I said, what the RN the encoder and decoder model is fit into the encoder step by step, and then get the embeddings time step by time step, fit into the decoder network time step by step, and then maximize the conditional probability of the target sequence given the input sequence. That's the whole idea of the encoder and decoder model. And then there's a lot of techniques that we can apply to improve the performance of the encoder and decoder model, attention, and then teacher force and other things. There's one thing I want to say about is that this is an architecture. This is not a model, meaning that we can apply this idea, this structure in any kinds of neural networks. For example, RNN. For example, linear layer. For example, CNN. It doesn't have to be the RNN model. One good example will be the transformer, which purely apply the linear network on the on language processing work, and it still has very good results. It outperforms the RNN model, like in the 2016, and the BERT model, which is a state-of-art language model, which just published last year in 2018. It holds the best results on general purpose language tasks, on many language tasks, and is still not using the encoder and decoder frameworks without using RNN. So they are purely linear network. They use the idea of encoder and decoder model, and then this still has the best results in the field of language processing. So So the point is that the encoder and decoder is not a model. So I write model here, but it's actually not a model. It's the idea of framework, how you're going to build your framework here. And the transformer is purely linear network to process language, which I already talked about. So this is just a picture of the transformer. I believe Professor is going to talk about this transformer in the future lecture. Like I said, they purely use linear network to process the language. Didn't use the RNN, and it's very powerful. It outperforms RNN in many language tasks. And that's it for today's slides. Let me give you a brief example on how to implement the encoder and decoder frameworks in the PyTorch framework. So the general idea is that we're gonna implement a network that contains a encoder and an decoder, and then we're gonna train them jointly. Can you guys see that, or need more zooming? Okay. Good. Okay. So the idea is that we're gonna have an encoder and a decoder in our network. So for example, my network. This is gonna be the network that I use in the training method. I'm gonna say I'm gonna train on this my network. I'm gonna do the back propagation through the my network. That's the one you're gonna use outside the model.py file. So in this my network, I have two parts. I have encoder, which I create as encoder, give the source vocabulary, and then the embedding size. The decoder is also, I have a decoder here, gives the target vocabulary size and the output size. And then I have a linear layer at the end of the my network that I was just trying to classify my output. And there's no magic. So let's take a look at the encoder class. In the encoder class, I was building a bidirectional LSTM. So purely just 3 LSTM layers here. This is my customer LSTM class. What it does is just reduce the size of your inputs. The code is actually here. I just built a LSTM using the given dimension, and then do it bidirectionally. And in the forward method, I just reduce the length of the input sequence, and then increase the future dimension of my embeddings, and then return the output. It's very, very simple. Reduce the length of my input sequence, and then double shrink the length, but have more width here. So I'm still storing the same amount of information, but I'm just reduce the size of it. That's what it does with this PB LSTM. And then in my encoder, I create 3 layers of the PB LSTM, and then has a dropout, which has a dropout rate of 0.3, and then have my MLP follow with it. In the forward, I'm just gonna pass through my X into those 3 layers of LSTM, and then do a dropout after that, and then return the output. So that's all I need to do for my encoder. At this step, I already has the embeddings for my framework. And then in the decoder framework, again, it's exactly the same thing. I'm building those layers and then return the results. The whole idea I was trying to show is that the encoder and decoder are just 2 LSTM networks. It can be exactly the same thing. You can still get very good results. The reason behind this, there's no common sense on why it outperforms so many models, but there's some intuition explanation for this is that the encoder is able to extract the features, the time sequence features into fixed length, so it somehow understands the language semantically and syntactically, and it stores this piece of information into the embeddings. And the decoder is trained to use this information to give us good results. So that's the whole idea. And what you're gonna do in the main class is you're gonna create an instance of this my network class, and then you're just gonna train it as normally. There's no magic here. So that's the whole training. That's the whole building process of the my network, and then you're gonna use this in your homework 3 and homework 4. Any question at this step? I know it's identical to frameworks. I was just trying to cut this simple because the idea is that you can have 2 identical encoder and decoder in your framework. It's totally fine. The point is not here. And next, I'm going to show you a more complicated, more powerful network that not only contains the encoder and decoder, but also contains the attention model. The major modification will be in the decoder part. So instead of only have the identical network, I'm gonna add a attention model here. That gonna tells me which part of the input sequence I should pay attention to. Another modification is in the encoder part. Instead of having one MLP, I have two MLP here. Each of them will X will pass them separately. Passing through the first one, we'll get the keys. Passing through the second one, we'll get the values. And we're gonna return both the keys and the values. So in the decoder part, it's the same thing. We have the keys and the values passing to our forward function. We're gonna pass these keys and values into the attention. Don't worry about the attention. It's gonna be covered in the next lecture. And then we're also gonna present the attention in detail, in PyTorch in detail in the next recitation. So don't worry about the attention. So just bear with me. Sorry about that. So passing the keys and the values into the attention gives you the context. The context contains a piece of information indicating that which part of the sequence of the input sequence I should pay attention to when I'm trying to decode it. And I'm gonna get my embedding Y. Embedding Y, remember, is the ground truth, right? The ground truth, the target sequence that I want. So a more complicated version will be I have a for loop here that has the same that iterates the same length of the target output. I'm gonna getting the embedding yi at each time step, and then I'm gonna concatenate it with the context that I generate from the attention. So right now, this X contains the information that not only has the original text information, but also has the attention information. It knows where to pay attention to along a sentence. So this X is more powerful, contains more information compared with previous models. And then it's the same thing. I'm gonna pass this X through different layers of LSTM. And then since this is just each time step, it's not the whole sentence. So I create a result list. At each time step, I'm gonna append this output into my results. So when I get out of this for loop, I'm gonna convert this results list as a NP array. This result right now has a whole sentence generated by my network. So that's a more complicated version, and that's gonna be the version you're gonna use in your homework 3 and homework 4. That's just a basic idea. It's not exactly the same thing you're gonna implement for your homework 3 and homework 4, but the idea is the same. You're gonna do it time step by time step, and you have to use the attention map to improve your performance. So I guess that will be it for today's recitation. And then there will be a second part of the recitation, which already posts on Piazza. We're going to cover the CTC loss in that recitation. And hopefully that will be very helpful when you are trying to implement your homework 3. And I believe you guys have 25 days to do the homework 3, and then a whole month to do homework 4. Homework 4 is going to be very painful, and because you still have to do a project at that time. So if you have time, if you want to do some work during the spring break, I think that's a good idea. Thank you, people.